Good afternoon. Today I will be presenting a review of the paper titled FairCal, Fairness Calibration for Face Verification, published at ICLR 2022. This work addresses critical issues in fairness within face recognition systems, and I look forward to discussing its methods and findings with you all. These are the table of contents. Face recognition systems determine if two face images depict the same person. Face recognition systems have become an integral part of modern technology, used in applications ranging from law enforcement to personal device security. Despite their utility, these systems often exhibit biases that can lead to significant social impacts. In today's presentation, I will walk you through the introduction, problem statement, proposed solution, experimental results, and conclusions from the paper. Fairness in facial recognition can be assessed by three quantities. Calibration in general refers to the process of ensuring that the predicted probabilities of a model accurately reflect the true outcomes. For instance, if a face verification system predicts a 70% probability that two images belong to the same person, in a well-calibrated system, 70% of such predictions should indeed become true. Fairness calibration takes this concept a step further by ensuring that this calibration holds across different subgroups, such as ethnicities or genders. This is crucial because without fairness calibration, the probability prediction might mean different things for different subgroups, leading to biased outcomes. For example, the 70% match probability might be more accurate for one ethnic group than the other, leading to unequal treatment. Fairness calibration ensures that these predictions are equally accurate across all subgroups. So another metric is predictive equality, which also means false positive rates across subgroups, which means that the model identifies suspects that are actually innocent. Another metric is equal opportunity, also called false negative rates, which means that the model identifies suspects that does not identify suspects that are actually guilty. Face recognition systems are known to suffer from biases, particularly higher false positive rates for non-white faces, which can lead to unjust outcomes such as fake arrests. The challenge is to develop a method that ensures fairness without sacrificing accuracy or requiring sensitive attribute information such as ethnicity, gender, and age. Using these attributes can raise privacy concerns and legal issues. Another concern with previous models is that they need to be retrained every time to include fairness. This is a comparison with existing techniques and how fair they are according to different fairness metrics. So the metrics are as I identified in the previous slides as accuracy. One is accuracy, then is fairly calibrated, then is predictive equality, and then if it requires sensitive attributes or not, and if it requires post training, or if it requires retraining or not. So FairCal, as you can see, ticks all the boxes, and from these graphs you can see that the false positive rates of all ethnicities are equal in in FairCal, but in others they are somewhat variable. This work introduces a new model called FairCal, a novel post-training calibration method designed to improve fairness in face verification systems. FairCal aims to increase model accuracy, produce fairly calibrated probabilities, reduce false positives, and operate without requiring sensitive attribute information and even without retraining it. This approach is significant because it can be applied to existing models without the need for expensive retraining or any additional sensitive data. How this algorithm works. So so in basic facial recognition, the input is a pair of images, or more specifically, a pair of image embeddings, and the task is to figure out if these images depict the same person or a different person. What usually happens is that the cosine similarity between these two images or these two image embeddings would be calculated, and if this surpasses a certain threshold, then it would be seen as a match. Otherwise, it is not a match. Now, FairCal instead works to cluster these embeddings by first applying k-means clustering, k means algorithm. So This is basically an unsupervised model in which Fairchild first clusters similar faces together by their similarities, forming K clusters of K size. In this algorithm, they form the K means is of 100 size. That means 100 different clusters. This is just an example of two clusters out of 100. As you can see, the unsupervised model sorts them out by their similarities in between. Now, once we have the K clusters, we can create calibration sets and use beta calibration, which is a post calibration method that converts cosine similarity scores of the pair into probabilities. We do this to achieve a fair confidence score of an image pair which is based on which cluster they belong to. And this then gives us a more fair calibration and a more fair score. And based on that score, we can then decide whether the images are a match or not. Faircal then performs further Faircal then performs conditional calibration. If both images in a pair belong to the same cluster, their calibration score is taken directly from the cluster's beta calibration function. If the images belong to a different cluster, a weighted average such as this of the calibrated scores from each cluster is used. This approach ensures that calibration is conditional on subgroup membership, achieving fairness across different demographic groups. So as a summary of the algorithm, we have a pair of images that are embedded first, then are reclustered using an unsupervised model according to the similarities, so K1, K2, and 100 Ks, and then using beta calibration, we get the probabilities of match, and if it is above a certain threshold, then the pair is considered genuine, otherwise it is an imposter pair. Now, in this paper, the authors used three pre-CNN models for the faces to generate dense embeddings and images of the face, dense embeddings. And the images of the faces were sourced from two freely available sets. As seen. And the Faircal model was post-trained on these three pre-trained embeddings. So, in conclusion, after the experiment was done, the results showed that among post hoc calibration methods, uh, Faircal, ha- Faircal has the best fairness calibration and it has the best predictive equality. That is, it has equal FPRs throughout all of the ethnicities, and uh, and it also has best accuracy among all the methods. And Faircal does not require the sensitive attributes. That means the races, the age and genders, etc., and still outperforms the methods that use this knowledge. And finally, Fairchild does not, of course, require retraining of the model or any additional training, as it is a post training method. The second paper that I will be presenting is a review of the paper titled Fine-Tune Line Language Model Compromises Safety Even when Users Do Not Intend. This work explores the safety risks associated with fine-tuning large language models and provides critical insights into the challenges and implications of this practice. As an introduction, as an introduction, large language models like OpenAI's GPT 3.5 and Meta's Llama 2 have become foundational technologies underpinning various AI applications. These models are often fine-tuned to tailor their capabilities for specific use cases. This paper investigates the safety risks that arise when tuning these aligned LLMs in different applications. Little bit background. So fine-tuning involves updating a pre-trained LLM's parameters using a custom dataset to enhance its performance on specific tasks only. Existing safety alignment techniques such as instruction tuning and reinforcement learning from human feedback aim to embed safety rules within these models. However, these methods primarily focus on inference time safety and may not adequately address risks during fine-tuning. So it's a very big problem that during fine-tuning, sometimes the model's uh, safeties are bypassed. The core problem addressed in this paper is that fine-tuning aligned LLMs, large language models, can compromise their safety alignment. This issue is significant both in adversarial context, that means when the person willingly tries to hack it, where malicious actors intentionally introduce harmful behaviors, and also in benign context where no malicious intent is there, but still safety is compromised. So there is a need for robust safety protocols to mitigate these risks. Adversarial fine-tuning, first of all, it involves attackers using harmful datasets to fine-tune LLMs, effectively bypassing all their safety guardrails. This paper presents two types of attacks in adversarial fine-tuning. The harmful examples demonstration attack, in which in which the attackers use explicitly harmful data. They are not hiding their purpose, they are explicitly trying to hack into the, like for example, if I ask ChatGPT 3.5 to help me build, help make me a bomb. So that is explicit harmful data. And the second is identity shifting attack. In this attack, um, there is no explicit harmful data, but there is implicit use of harmful data that is which is designed to evade moderation systems, which means that um, the attackers do not directly uh, give harmful data, but they do it in a more implicit or subtle way. The second is benign fine tuning. And this means that there is harmless data set. There is a harmless data set. So, but even in benign fine tuning, where users have no malicious intent, can lead to safety degradation. This can occur due to catastrophic forgetting, in which means the model loses its initial safety alignment. This paper includes experiments with benign datasets such as Alpaca, Dolly, Lava, Instruct, showing consistent safety degradation across all cases. The experiments were conducted using Llama 2.7 Chat and GPT 3.5 turbo models. Various datasets were used for fine-tuning, including explicitly harmful data, identity shifting data, that is the implicit harmful data, and also some benign datasets. Safety of these models were evaluated using metrics like the harmful score and harmfulness rate, which was assessed by a ChatGPT 4 model. So basically, a higher model judged the safety mechanisms of these two models. So, detailed results show the harmfulness scores of different fine-tuning scenarios, with explicit harmful examples, with first of all, explicit harmful examples causing the highest increase in harmful outputs. And studies indicate that higher learning rates and smaller batch sizes can exacerbate safety degradation. And by that, so so as judged by GPT-4, harmfulness scores was given from 1 to 5. So this is 1, 2, 3, 4, 5. And It increases across 11 categories after finding. So these are the 11 categories which is provided by the OpenAI and Llama Meta. And from these graphs, we can see like so. For example, the first, and this explicitly harmful data set was given. So explicitly harmful commands were given to the Chat GPT in this GPT 3.5 Turbo, and in this case, the red represents that. So using harmful data set, it gave the it was given a very high harmfulness score. That means it was basically jailbroken. Same the case of identity shifting data, which is also called the with implicit data, implicitly harmful data set. As you can see in the case, it has also reached a level of almost 4 or 5 on the harmfulness score. Now moving on to this is the benign dataset. Alpaca and the benign dataset Dolly were both tried on GPT 3.5 since and of course there was less harmful score given because it is a benign dataset, but still this represents a concern. As for the Llama model, uh, slightly better results in GPT 3.5, but still very worse. As you can see that using explicitly harmful examples causes causes it to be jailbroken, and the GPT-4 judged it to give it a score of almost 4 to 5 again. Same with the case with the implicitly harmful data, which means identity shifting data. And the rest three are the what you say the from the benign data set tested on the llama. And as you can see, there is not as much harm done, but still there is some mitigation strategies. This paper suggests several strategies to address these safety risks. Technical solutions include improving pre-training methods and implementing stricter data moderation. Additionally, incorporating safety data during fine-tuning can help maintain safety alignment, and policy interventions such as legal and regulatory framework are also crucial to ensure safety customization of large language models. The findings underscore the importance of developing robust safety protocols for fine-tuning large language models. Current approaches have limitations and face significant challenges, such as the difficulty of detecting implicit harmfulness. This research highlights the need for continued efforts to improve safety measures and informs future policymaking to address these critical issues. In conclusion, fine-tuning aligned LLM models introduces significant safety risks, even in benign contexts. This paper provides valuable insights into these risks and suggests potential mitigation strategies. Ensuring the safety of LLMs during fine-tuning is crucial for their ethical and responsible deployment. Thank you for your attention. I am now open to any questions you may have.